So remember, well, for me, about 35 years ago when you were 15 years old on a summer day looking up in the stars, the whole galaxy displayed out in front of you, wondering, am I the only one here? Are there other planets up there? Are there other people up there? Well, fast forward, in my case, 35 years, and we now have the answer to that. The Kepler Spacecraft, which is a telescope, a planet-finding telescope, gives us the ability to identify whether or not there are planets around other suns, and also give us the ability to determine whether those planets could potentially support life. And by support life, I mean have water. Because what we've learned on Earth is that water is the key essential element to having life. We've never found a living organism that can exist without water. It's a ubiquitous requirement for life. So the Kepler spacecraft has actually determined that pretty much all those stars that you saw out there on that summer night have planets around them. And a good number of them have planets that are very similar to Earth. So if you look at this plot here, you can see that it has basically the radius of the planet and the mass of the planet. And the Kepler gives us the ability to do that. And from those two data points, we can determine whether or not these planets have water on them. So if you look at the two bottom curves there, one of them is Earth-like planet, which means it's a mixture of water and rock. And the next curve up is a 100% water planet that's just made of water. And then above that, you get into sort of the gas giants, the bigger planets that are all made of gas. And as you can see, this is kind of an old plot. There's at least 2 or 3 planets that are Earth-like. I think actually right now we're up to several hundred planets that we've identified that are Earth-like, meaning they have water on them. The one in red is probably the most important one because that's a planet that orbits one of the closest stars to us, which actually doesn't mean it's very close. It's still very far away. So the Kepler concept is based on something that actually dates back a long time ago, which comes from our solar system, which is this concept of the habitable zone. And if you look at the blue crescent there, that's what's called the habitable zone. That's the area from our sun where you're not so close that all the water is going to boil off and turn to vapor, and you're not so far away that it's going to turn to ice. It's going to be so cold that it's going to turn to ice. And as you can see, Venus is too hot, so there's no liquid water on Venus, and Mars is too cold. Right? Mars just has ice on it. And outer planets are far too cold. Well, that concept has actually recently changed. We've actually been able to find liquid water on the moons of Jupiter, both the moons of Saturn and Jupiter. We've actually observed liquid water coming out in geysers from those moons. And also on Mars, our understanding has changed quite a bit. Mars is perhaps the most interesting of all those planets because we send a lot of robotic spacecraft to Mars, so we have a very good understanding of what's going on Mars. One of the most important spacecraft we sent to Mars was the Mars Phoenix lander. This was a very simple little spacecraft that just was capable of digging holes and taking pictures. And what it determined was that if you go to the North Pole of Mars and you dig down a few inches, you hit permafrost. And that's the picture on the right-hand side. Right-hand side there is a picture of some of the permafrost that was identified on Mars. Now, Mars, the pressure is very low, so it just sublimes away and immediately disappears. But that proved that there is water, at least ice water, on Mars. And as you recall, the search for life is a search for water. That's the key to it. Another interesting observation from orbiting spacecraft are that in many places on Mars, around the rims of craters, we see what looks like episodic events of liquid water coming to the surface of Mars, where you see these rivers and valleys. So the picture in the upper hand left is the rim of a crater on Mars, and then there's successive blow-ups showing greater detail, and these would look like sort of riverbeds, very similar to what you might see in the Anaconda Desert, where it doesn't rain very often, and when it does rain, it causes huge problems. This is certainly not rain. What we believe is happening is that there's some geothermal energy, probably from radiation sources, that is melting permafrost ice and causing the ice then to run in liquid and then run down through the edges of the craters, and it immediately sublimes, so you don't have lakes or anything, but it immediately evaporates up and disappears. From the Mars Curiosity rover, we have the ability to actually go to Mars and get rocks and drill holes in the rocks and take some of the powder from drilling the holes and analyze those. And what we see pretty much ubiquitously in all soils on Mars is that there's a lot of water in those soils. This is water that's bound to particles of soil material. Perhaps more important than that, we also see carbon, we see oxygen, we see sulfur, we see hydrogen. and the atmosphere of Mars is about 2% nitrogen. All of you sitting in here are made up of carbon, oxygen, sulfur, hydrogen, and nitrogen. That's what you're made up of. That's what you're composed of. So we have water. We have some evidence that that water may be liquid at certain times, and we have all the necessary elements to produce life. We do not know if life exists there or not. There's one more tantalizing bit of evidence that comes from remote observations, which is methane in the atmosphere of Mars. This is a plot, a false color plot that shows the red color is methane observations from an orbiting spacecraft, but we also get them from ground-based telescopic analysis. And we see these methane clouds. Methane decomposes, it's very reactive, doesn't stay around for very long. We see it as a seasonal. In the summer, we see methane clouds and goes away in the wintertime. Also, when Mars has very cold summers, we don't see the methane clouds. They're not there. And this is an indication that this methane is being generated by some sort of process that exists on Mars right now. And we just came from a sludge treatment talk. One of the best ways to produce methane is decomposition of organic matter. It can also be produced from chemical processes like the Fischer-Tropsch reaction. That's a thermal rock reaction with temperature. Mars is considered to be a somewhat dead planet, meaning it doesn't have a molten core. So it's not like here on Earth where that's a large source of methane. Also, those methane clouds are associated with locations. If you look at the plot down to on the bottom right-hand side, where you see evidence of, for instance, water-based minerals. Minerals that can only be formed from evaporating water. Also subsurface water, which is measured by hydrogen, the identification of hydrogen, and volatile-rich soils, which also is an indication of some sort of process going there. So if the search for life is all based around water, there's a good indication that there's water on Mars, and there's also a likelihood or a probability that there might be at least historically been life on Mars or that life may exist. However, to fully answer that question is going to require us going to Mars. Our robotic technology is not that good. I hear a lot of people here talk about artificial intelligence. And I can assure you there is no such thing as artificial intelligence. It does not exist. Right? We do not have that capability. We build robots, we send them to Mars, they do what they're programmed to do, and they can't do anything else. That's it. They cannot think, they cannot adapt like a human being can. What we need to do is send a graduate student to Mars. That's how we're going to get the answer to those questions. So, if we're going to send humans to Mars, then we have another water problem, right? This is a chart that shows the mass required to keep a person alive. In the space business, all we care about are kilograms on the launch pad. We don't care how much those kilograms cost to make. We don't care what they are. We care about how much they weigh because they have to be launched into space, and that's what our cost structure is. We got to buy a rocket to put those kilograms in space. And water is your big mass. If you're going to send humans to Mars, water is going to be your #1 cost to keep them alive for long periods of time. So water recycling is very important to NASA, and NASA has a long history of doing technology development in water recycling, dating back all the way back to 1962, which was when they really started a focused effort in water technology development. Our premier test bed right now is the International Space Station. If you have kids who want to be astronauts, they better be prepared to drink their own urine because that's the only water we have on the International Space Station. Recycled urine and also humidity condensate. We recycle those. So this is, I know it's a forbidden term in meetings like this, but this is a true toilet to tap water recycling system, meaning the pipe connected to the toilet is also connected to the faucet. And within 3 minutes, if you go to the bathroom, within 3 minutes, you're going to drink your urine that's been recycled. We also do full carbon sequestration on the International Space Station. We do trace contaminant control, smell, odor control. It's all solar powered. It's an example of one of the most sustainable systems that the Earth has ever produced, aside from the environmental tragedy of launching it and getting it up there into outer space. This is a picture of the water recycling system on the International Space Station. It's basically a big machine. It's a physical chemical technology. We use vapor compression distillation to treat the urine. And then we have something we call multifiltration beds, which are a combination of different types of absorbents to treat the byproducts. And then we have a thermal catalytic reactor that's very similar to like a wet ox reactor that then used to ensure that the water is sterile, and also if there's any trace organics that pass through the other systems, it removes those trace organics. And you can see a picture there on the bottom. That's the first time they drank. The astronauts had the pleasure of drinking their own urine back in 2009. You can see how happy they are. Big smiles all around. That picture is probably not correct. It should be on its side or upside down or something like that, because these technologies are very specialized because they're designed to work in microgravity. You can imagine how complicated it is if I went and got the toilet out of the bathroom and bolted it to the ceiling and told you all, that's your toilet. That's what you're going to use. It's pretty complicated. No pumps work in microgravity. Connectivity sensors don't even work in microgravity. The complexities associated with building technology to operate in microgravity pretty much requires starting at ground zero and building from there on up. In fact, the entire International Space Station really isn't a habitat. What the International Space Station is a big, huge machine, and humans live inside that machine. And we've been operating it now, at least the life support portion, since 2009, and we've learned a lot. We have a term that we use to describe this called the romance of the machine. And that means that we, as modern people, have come to expect machines to work for us. You drive to work in a car, you fly in an airplane. But machines have fundamental limitations, fundamental problems, which is that they break down. They break down all the time. Maintenance is a huge problem for us on the International Space Station. What we've learned from the International Space Station is that if you're going to go to Mars and you're going to colonize Mars, you're not going to be able to take machines along with you because they just do not have the level of reliability that's necessary for that type of mission. On a Mars mission, the shortest duration we're talking about is about 3 years. It takes 1 year to get there. You have to stay there for 1 year due to orbital mechanics, and it takes another year to come back. So we need to have machines that are going to work for a minimum of 3 years, right? So in the water recycling, that's sort of our advanced development programs right now are really focused on that. And if I can make a water recycling system that'll work for 3 years with no maintenance, no human interaction, well, I can probably do 5 years then. If I can do 5 years, well, hell, I could probably do 10 years if I could do 5 years, right? And if I can do 10 years, what's stopping me from 20 years, right? The question is that possible? Could I make a water recycling system that's good for 20 years, no human interaction, no maintenance? Could I make one that lasted for 80 years, potentially? Well, the answer is, of course, yes. You guys are all examples of water recycling systems that have lives of 50 to 80 years, typically. There's no small intestine maintenance that you have to go through in that 80-year period, right? Evolution has gone down a path to optimize your body to be a water recycling system, and you can seriously abuse it. You can put tacos into it, right? You can go down to Tijuana, eat a taco on a little stand by the side of the road. You had horrible diarrhea, but you'll be fine. None of those bacteria, none of those viruses will get into your blood. You'll be fine. You can be a little kid. You can eat a paper clip, right? And go to the doctor. What's the doctor going to tell you? Say, but this, wait, it'll be fine. Give it some time. It'll come out. Don't worry about it. So that's where a lot of our research is going on right now. And so what we're really focusing on a lot are biomimetic technologies, trying to get away from the concept of these machines that break down all the time and to go to more reliable technologies. So we have a project right now where we actually are developing a small intestine-based water recycling system. So a lot of our work is focused on forward osmosis because that's how your small intestine works. It uses forward osmosis. And we also are doing a lot of work developing what are called living membranes, which are membranes where we genetically engineer bacteria, embed them into the membrane material, and then they excrete the material that the membranes are made out of, mainly lipids and fatty acids primarily, live off of the feed, with the organic content of the feed and the minerals that are in the feed, and just create a membrane that's capable of living for long periods of time. Self-cleaning, removes calcium scale off of it, has the ability to deal with organic fouling just the same way your small intestine does. We also are doing a lot of work looking at proteins in membranes, because proteins have evolved over that 3.8 billion years that life has been evolving to be the perfect structure for doing water separations. In addition to that, we can regenerate proteins very easily. We can have genetically engineered bacteria that express proteins, so we can make membranes that are sort of self-regenerating membranes. This is all kind of basic research. You probably won't see it for 20 years or something out in the future, but this is the technology that's going to sort of enable that colonization of Mars, where we have the opportunity to have a clean slate on how we do water recycling and how we do solid waste treatment. We don't have to use those old paradigms. We can take a new approach into what we're doing because we're starting from scratch. We also do technology transfer. Taxpayers pay our costs, and so we need to give back more than just just going to space. We also need to solve terrestrial problems. This is an example of a water recycling system in an office building in Sunnyvale, California. It's a 250-person office building. It uses gray water recycling. We take all the gray water from the building. We purify it to potable levels, but then we're just using it for toilet flushing. We don't want to make everybody drink the recycled water. It's a little bit too much, and they don't drink enough water to really make it worth doing anyway. This is another example of Army forward operating base system. So this was another water recycling system that was developed, and this was designed for a forward operating base. It's a 150-person forward operating base facility designed to be airdropped into the site. Had to be completely automated so that you didn't have to have a trained operator, could just be operated by a soldier out in the field. Had to go from being delivered to operating within 1 hour of delivery. We've also done a lot of work in food processing industries as well. They tend to have very difficult wastewater streams to develop. We've done some work with distillation systems and some work with forward osmosis systems in the food processing environments as well. We've done a little work in desalination, and our work in desalination has primarily been focused on developing desalination systems that don't have a negative environmental impact. So these are systems that don't produce a concentrated salt byproduct, and that you don't have to remove the solids out of the feed, so you don't kill all the entrained organisms that are inside of them, and so you don't end up with a lot of byproducts that are going to a landfill as a product of that. And then what we're working on right now are primarily developing technologies for commercial and residential office buildings. State of California just went through a drought, and that really sort of changed the public's opinion about water recycling, and now it's acceptable to build skyscrapers that recycle the water inside the buildings. And so we're doing a lot of work for some of the high-tech companies that are in the valley in that area, and then a lot of developers in the San Francisco Bay Area who are wanting to build new projects. And the city and the state are saying, you know, we're not going to let you build those projects unless you can put water recycling integrated into those buildings. And that's where I think really the future of this type of technology really lies is in those applications, because it's easy to calculate a return on investment on those kinds of investments. If you want to develop a piece of property and the answer from the local community is no, we're not going to allow you to do it, and if you integrate in water recycling systems, then the answer is yes. It's easy to calculate the financial benefit of those kinds of projects. So that's where I'll leave it. Thank you.